Good morning.
Morning, Christian. Good morning, everybody, and welcome.
Morning.
Good morning. Okay, now now we can start our recording. Okay, guys. So we can say that we're going to start off with Doppler. Okay. Now, guys, what Doppler mainly is going to be, we can say, it's okay, that's going to be, it's okay, an ultrasound testing. What do you mean by ultrasound testing or scanning? Let's put it this way. Okay. But what is the goal in which we measure the velocity of blood? Is that clear? So Doppler primarily is not intended to, yes, okay, you can say, create an image. Okay, your goal in a Doppler is not to create an image. Well, okay, as you create an image, but within that image, that's okay, what the Doppler mainly is used for is to, in most instances, you can say, it's okay, 99% of the instances are going to measure, it's okay, the velocity of blood. Is that clear?
Yeah.
Okay. Okay. Now again, yes, okay, what we did in chapter 17, when we talked harmonics, we said, okay, yes, that we had a main frequency. We also, as okay, refer to that as the resonant frequency. Or yes, okay, in chapter 14, we also call that, 17, sorry, we also refer to that as being the fundamental frequency. But what was it that all these frequencies were? These were mainly as okay, what we're going to call as okay, say, or the frequency, because there's okay, the frequency of the transducer. Yeah, okay. Okay. Or mainly as okay, if we said that okay, yes, we had a frequency, we had a transducer. The frequency of the sound wave that the sound that the transducer here was going to be transmitting at was going to be as okay, the main frequency, the resonant frequency, the fundamental frequency, or the frequency of the transducer. Is that clear? Is that clear?
Yeah.
Good. Now, what we are going to receive back. So what we mainly as okay, we'll call these frequencies here as okay, we will call them the transmitted frequency. Or we can as okay also call it the transducer's frequency. Did you guys get that?
Yep.
Good. Now when this sound wave here, yes, okay, is going to hit blood, it is going to, yes, okay, reflect back. Yeah, okay. And what we in this chapter here is okay, we'll do is going to, yes, okay, say that, okay, yes, that the frequency at which the sound is reflecting back that is what we'll call the reflecting frequency. Okay, guys. So yes, okay. One thing that we will be doing to is okay, primarily is okay, get into yes, okay, just the basis of like what is it that a Doppler is going to be. Yes, okay. To begin with, yes, okay, mainly yes, okay, we'll refer to these two frequencies here. The transmitted frequency and okay, yes, the reflected frequency. Okay. And actually, yes, okay, with help of those, with help of these two frequencies here, we actually, yes, okay, will be able to, yes, okay, get what we will call a Doppler frequency. Now, this Doppler frequency may also, yes, okay, be called the Doppler shift. Did you guys get that? Okay.
Yeah, so Doppler frequency is the,
Also known as a Doppler shift.
but it's the transmitted frequency plus reflected frequency.
It's going to be the differences of those.
Okay.
It's going to be the differences of those. Now, guys, some of you will say, so why didn't we talk about a Doppler frequency earlier in the previous chapters? Because, okay, even in the previous chapters, what was it that we had? Well, okay, yes, of course, the transducer is going to, yes, okay, transmit at a frequency, right? Okay, the frequency at which the sound was produced by the transducer and transmitted into the tissues, that was going to be the transmitting frequency. Okay, and we mainly said that, okay, yes, that's frequency at which the sound wave was going to reflect back is the reflecting frequency. Okay, but in all the previous chapter, what is that we have been talking about is pretty much, okay, as just the physics of, let's put it this way, as okay, if we were scanning, yes, okay, objects which were stationary. objects, topic, tissues, etc., etc., which did not change their position, like your lungs, your bones, muscles, even yes, okay, a blood vessel, it doesn't change its position. But the thing that changes its position is the blood that runs in those blood vessels. So what we actually is okay will be seeing in a Doppler is that your transmitted frequency or your transducer's frequency is going to be different from the reflected frequency when it hits moving blood cells. Okay. And it's going to be as okay based on the difference between these two frequencies here that we get okay as what we'll call a Doppler frequency, or which we also refer to as a Doppler shift. Now, guys, it may sound crazy, but it's okay when an object is moving. Let's say it's okay, you are standing on the platform for a train station. This is a platform. And okay, yes, somebody was standing here. Yeah. Okay. Now you may, yes, okay, see that, okay, yes, that the train is approaching. Okay. Now, yes, okay, as it is approaching. Now, two things will happen. You can make says, okay, that, okay, yes, the frequency at which you hear, yes, okay, the engine car, or yes, okay, the sound of the engine is going to become more and more and more and more frequent. But here we can mainly says, okay, that it actually is okay, increases in loudness as it approaching you. Okay, so here is okay, we can say it's okay, the audible loudness that mainly is okay increases as the train is approaching you is mainly as okay due to a Doppler shift. Okay. Now, for instance, okay, if this train came and it's okay, got on a standstill in front of you, didn't move as okay either in this direction or in this direction, but it was at a standstill. Okay. Now it's not going to be producing as okay a sound which is going to as okay change in its intensity and or frequency. Now, ultimately, as okay, since as okay, at some point, as okay, this train here, as okay, will start moving again. Okay, that was not the train that you were waiting to catch. Okay, but as okay, it leaves. And what you mainly see is okay, as it moves away from you, as okay, the loudness or just okay, the sound that it was produced by the train just gets dimmer and dimmer and dimmer and dimmer. And that's again, yes, okay, going to be as okay due to a Doppler shift, as we may call it. Yeah, okay. So practically, yes, okay, we can have two. Oh, shit, sorry. Hold on, what I'm going to do. Practically, yes, okay, we can have two kinds of Doppler shifts. Or let's say three. We can have, okay, as when the train was moving towards you. That is going to be as okay, a positive Doppler shift. Yeah, okay. You can have another kind of Doppler shift, which means okay, was when the train in this case is okay was moving away from you. So that's going to be, okay, the negative Doppler shift. Yeah, okay, and we can say, okay, the third, although not that relevant, but as okay, we can also have as okay, we had a train, for instance, as okay, or the structure which previously okay was moving was at a standstill before you, in front of you. Okay, and that is going to, it's going to be as okay, where we say it's okay, it's not, it doesn't move towards you, it doesn't move away from you, and that's going to be as okay a zero Doppler shift. Did you guys get that?
Yes.
Good. Okay. Now, again, yes, okay, guys. In this chapter here, is okay, we will be using two terms. One is going to be as okay, what we will call or refer to as the source. Now, our source here is going to be as okay, what it does has been in the previous chapters where we talked about source is going to be the transducer. Whereas, okay, as and the others, yes, okay, the other term that we may come across is going to be as okay, the reflector. And our reflector here is going to be as okay, be what causes the reflection, and that's going to be the red blood cells or the blood cells. Okay, so as I say, it's okay, we mainly had two major types of Doppler shifts. One was going to be as okay, what we will call a positive Doppler shift. Now, as far as the definition goes, we will mainly say as okay that a positive Doppler shift is when the deflector, which is going to be as okay your red blood cell, because as okay moves towards the source, which is going to be as okay your transducer. Okay, that is one way to look at a positive Doppler shift. Or you can also put it this way, that a positive Doppler shift is when the distance between your reflector, which was okay as the red blood cell, and the source, which was your transducer. When that distance increases, that can also be referred to as a positive Doppler shift. Did that make sense? If you look here, that okay, yes, you can say, okay, as the train was moving towards us, okay, where you were standing, but okay, it moves towards you. So that was a positive Doppler shift. Okay, or saying that's okay, it moves towards you, as okay, from each span of second or time that passed, the distance between you standing on the platform and the train actually is okay reduced. So when the thing is okay, when the distance between you and the train decreases, that mainly means that okay, yes, there's a positive Doppler shift. Mainly because okay, that object which is moving, it moves towards you. Did you guys get that?
Yep.
Whereas on the other hand, guys, we can say as okay, a negative Doppler shift. Now, please keep in mind, guys, okay, that these Doppler shifts here also can be called Doppler frequencies. Okay, which can be positive and which can be negative. So it's okay, they can also be called Doppler frequencies. Okay, but when is it that we actually have okay as what we can call as okay a negative Doppler frequency or a negative Doppler shift? That is going to be is when the again it's okay, we can say it's okay the reflector. Which in our case is okay when we scan is okay moving blood or flowing blood, or reflectors is going to be as okay the red blood cells. Okay, but now these red blood cells here is okay. It's okay, they moves away from the source. Which in this case is going to be a transducer. Or we can even, yes, okay, word it this way and say, yes, okay, is when the distance between, yes, okay, what was our reflector, which is the red blood cell, and the source, which in this case is okay, was the transducer. When that distance is increasing. Did you guys get that? So if we looked here, yes, okay, you still standing on the platform, okay, and now yes, okay, the train just go. Now as it moves away from you, what is going to happen? The distance between you standing there and the distance of the train is increasing. Why is that mean? Yes, okay, because now it is moving away from you. So whichever way you want to take it, it will be considered to be a negative Doppler shift. Clear? Okay. But if you're standing here, the train is right in front of you, not moving right, not moving left. Okay. We can mainly, yes, okay, see that will be, yes, okay, a zero Doppler shift. Any questions? So for now, please, guys, when I say for now, because it's okay, it's going to just okay get supplemented later on. But what we mainly can say is that, okay, yes, for now, your Doppler shift, or we can mainly say, okay, say, when will we have a positive Doppler shift? When the blood cell or when the blood is flowing towards the transducer. So when blood flows towards the transducer, that will be referred to as a positive Doppler shift. When the blood flows away from the transducer, that will be referred to as a negative Doppler shift. Is that clear? Okay, guys. Now, do any of you have any idea where the hell they got this technology from? To use sound waves to detect whether things are approaching you or moving away from you. Things that may not necessarily as okay produce a sound as such. Things that you physically might not have been able to see. Or you still know that, okay, it's approaching you, or okay, it's getting away from you. No idea? Have you guys heard of submarines? Now it's easy, yes, okay, if you are standing on the deck of a ship and say, well, okay, there's a ship over there. It's sailing towards us. Or we on this ship here and there, yes, okay, they on that ship here is okay. We are approaching one another because you physically are able to see, right? That gets closer and closer and closer and closer. But in submarines, that's okay, you can't be standing on the deck. Clear? So how would they know that, okay, as another submarine is approaching you with this technology? That's primarily as okay, where it was derived from. So you can mainly say, okay, if you ever listen to us, okay, or watch any of those war movies and so on, so on, so on, documentaries, you may hear that, okay, as they catch something on the radar and the sound go, what does that mean? That the frequency at which you are receiving the signals ends up being greater than the frequency of the at which is okay you are transmitting the signals. And what does that mean? That your submarine and that other submarine actually is okay are approaching one another. Okay, so guys, now we're going to just okay be doing yes okay a lot of ups and downs. But just to just okay get it straight, let's just say okay mathematically, how do we calculate a Doppler shift, also known as a Doppler frequency? Now, as I said earlier, that okay, yes, the Doppler shift, which we also yes okay call as okay a Doppler frequency. Yeah, okay. Mainly as okay is going to be as okay the difference between the reflected frequency being as okay subtracted from the transmitted frequency. Is that clear?
Yeah.
So what we mainly can say is, okay, yes, that no matter what, the difference of these two frequencies here is going to be as, okay, what we'll call the Doppler frequency or the Doppler shift. Did you guys get that?
Yep.
Good. Now, what we can say is that if yes, okay, your reflected frequency, if that is greater than the transmitted frequency or the transducer's frequency, this will actually cause that, okay, yes, you will have what we call a positive Doppler shift or a positive Doppler frequency. And what did we mean by the positive Doppler frequency? That was mainly going to be that, okay, yes, that the red blood cells moves towards the transducer. Well, now just remember this much. Or we could say as, okay, that the distance between the red blood cells and the transducer was decreasing. Did you guys get that?
Yep.
Good. Whereas, okay, as on the other hand, if we said it the other way around, that your reflected frequency is lesser than the transmitted frequency, that is going to give us, okay, what you would call a negative Doppler shift. And what did we mean by us, okay, saying a negative Doppler shift? That mainly meant that, okay, yes, for now, it's okay that the red blood cells is okay, they move away from the transducer. Did you guys get that?
Yeah.
Okay. Now, guys, to begin with, just okay, this Doppler shift here is called a Doppler frequency, mainly because okay, it is going to be as okay, be detected by the system using the unit of frequency, which is going to be hertz. It is just going to be as okay, the job of the system to convert this hertz into speed of blood. And okay, as expressing that in a unit of speed, which was going to be as okay, any distance of any unit of distance by unit of time. Okay. But the only thing that the system is okay, primarily is okay, gets It's a frequency of, yes, okay, reflecting back from the red blood cells, which may be, yes, okay, constantly increasing, or which is going to be, yes, okay, greater than the frequency at which the system was transmitting. And based from that, the system, yes, okay, or we would say that, okay, yes, that's mainly because that the reflector is moving towards the transducer, that the frequency of the reflections is going to be greater than the frequency of the transmission. And based on that, is okay, we determine that, okay, it's going to be a positive Doppler shift. Because it's okay, when we talk about, it's okay, the reflector frequency is still going to be in hertz, kilohertz, megahertz, whatever. So is your transmitter frequency. It's still going to be, as okay, expressed in hertz. Okay. But it's mainly as okay, the difference between these two that determines, that gives us, okay, what we can call as, okay, a Doppler shift or a Doppler frequency. You can say, okay, why a Doppler shift? Because it's a shift in the transmitted frequency. Okay. That we mainly will say, okay, is that a shift that, okay, that the frequency that we receives back, which is going to be reflected frequency, is greater than the frequency of the sound that was transmitted. That will be positive. Whereas, okay, yes, if it's the other way around, that the frequency of the reflections is lesser than the transmitting frequency. Okay, now that may just mean that, okay, yes, that the red blood cells were moving away from the transducer. Okay, so that's okay in those war movies or documentaries or whatever you call it, you may hear that it was then it just diminishes. Yeah, okay. So based on that shift in the frequencies, they determined that, okay, yes, that submarine that, okay, yes, was so close to us fled. Mainly because they said, okay, we're standing here, we're going nowhere. If they get too close, we're just going to the fire, missile or something, or a rocket, and okay, yes, demolish them. Did that make sense? So that is what they made is, okay, what they just transferred into ultrasound. And say, can we use that for as, okay, detecting or as, okay, determining not only as, okay, whether things approaches us or as, okay, get away, but as, okay, also use that to as, okay, determine as, okay, how fast it is approaching us or how fast it's getting away from us. Did you guys get that? Okay, so for now, guys, what we to start with, what we will mean by saying yes, okay, a positive Doppler shift means blood flows towards the transducer. Negative Doppler shift, blood flows away from the transducer. Okay. And what the hell? What? Oh, sorry. What was it that a Doppler shift was? That was okay. That difference between your reflector frequency being subtracted from the transmitted frequency. Yeah. Okay. But, with that said, if your reflector frequency was greater than the transmitter frequency, that makes it a positive Doppler shift. Whereas on the other hand, if your reflector frequency was lesser than the transmitter frequency, that gave you is okay a negative Doppler shift. So this slide here is a must to know. Did you guys get that?
Yep.
Okay, dear guys. So we can just say it's okay that Doppler shift, known as Doppler frequency, equals to the reflected frequency subtracted from the transmitted frequency. What was going to be as okay, your transmitted frequency mainly as okay, just the frequency of the transducer. Clear? Did you guys get that?
Yep.
Good. Well, we said that, okay, yes. Okay. When this one here was less and this one here was greater, that gave us a negative Doppler shift. Whereas, okay, if we went the other way and say it's okay that this one here was greater and this one here was lesser, that was going to be as okay, positive Doppler shift. Now let us just okay calculate some different Doppler shifts, and then mainly as okay try to as okay say as okay how is it that they will make sense. Now let us just say, for instance, that okay, yes, our transmitted frequency was 20 megahertz. Yep, okay. And in this instance, yes, okay, our reflector frequency was, let's say it's okay, 21 megahertz. Okay. Now when we, yes, okay, subtract these, we can mainly say that, okay, yes, what we got was the Doppler frequency, which was going to be 1 megahertz. Because the difference between these two here was 1 megahertz. But we mainly can say is okay because our reflected frequency was greater and the transmitted frequency was lower. Oh, yes, okay. You say, well, okay, I got $21. I spent $20. So what do you have left? I have $1 left. So your bank balance is still positive, right? Did you guys get that? So
Yeah.
in this is, pardon me?
I said, yeah.
Okay, good. Okay, okay. So in this instance, okay, what did we have? We ended up, okay, having a Doppler shift of 1 megahertz. Or we can say, okay, a plus 1 megahertz Doppler shift, which was, okay, the plus here is going to mean that, okay, yes, it is a positive Doppler shift. What did we mean by a positive Doppler shift? That blood moves towards the transducer. That what mainly called that, okay, yes, the frequency at which we are transmitting at versus, okay, the frequency that we were receiving reflections back, the reflecting frequency was greater than the transmitted frequency. But here we had a difference of 1 megahertz. Did you guys get that?
Yep.
Good. Now let's just say that, okay, yes, it was the same frequency with the same transmitting frequency. $20 megahertz. Now let us just say that, for instance, that in this case, as okay, the reflector frequency was 25 megahertz. Right? Okay. Now, of course, that's okay. Well, okay, yes, we had 25 megahertz that from which we subtract 20. Yes, okay, we are going to be left with 5 megahertz. And of course, that's okay, as we can see that, okay, the reflected frequency is greater than the transmitted frequency. Clear? Okay, that's what's going to make this here, okay, still be as okay, a positive Doppler shift or a positive Doppler frequency of plus 5 megahertz. Did you guys get that?
Yep.
Yes.
Good. Now, if we just do it the other way, we say, okay, let's say that we still have the same transducer. It still is okay, transmits at a 20 megahertz frequency. But in this case, here's okay, our reflected frequency is going to be 19 megahertz. Now the difference of this, now you have $19 and you spend $20. What's going to happen? Well, okay, yes, you're going to be, yes, okay, $1 negative. Mainly because you subtracted a bigger number from a smaller number, you are going to be negative. So this was lesser and this was greater. So that gave you, yes, okay, a Doppler shift of minus 1 megahertz. And what do we mean by a negative Doppler shift? That the blood actually is moving away from the transducer. Did you guys get that?
Yep.
Right?
Yes.
Okay, guys. Now, on the other hand, if we say, well, okay, well, the same transducer, let's say it's okay, same 20 megahertz. But now, yes, okay, your reflected frequency is going to be 15 megahertz. Okay. So when you said, okay, as I subtract 20 from 15. Okay. Now that's going to be, okay, the numerical difference is going to be 5. But mainly because you subtract a bigger number from a smaller number, you're going to end up in a negative. Or mainly we can say, okay, it is going to be negative because, okay, your reflecting frequency is greater than, is lesser than the transmitter frequency. So in this case, yes, okay, we're even going to, yes, okay, give you, yes, okay, a negative Doppler shift of minus 5 megahertz. Did that make any sense?
Yes.
Okay, guys. Now, here I'm just going to tell you something, yes, okay, just to explain it, or let's say it's okay to assume. Because now if I told you guys that blood is moving at a frequency of 5 megahertz, you're going to say, oh, what the F are you talking about? How is that going to make any sense? Right? I may say, okay, blood is moving at a frequency of, okay, minus 5 megahertz. Okay. No sense. Okay, so the value of frequency is actually, okay, going to, we can say, okay, be translated into speed. Let's just go with the speed first. And please, guys, do not come back to me and say, Mike, you said that a Doppler shift of 1 megahertz was equal to 1 centimeter per second, as far as speed is concerned. We're just going to use that value here just to make, let's say, okay, the conversion easier. Okay, did that make sense? Okay, so what we mainly can say is that if we can say, okay, for each megahertz in the Doppler shift, yes, okay, may equal to 1 centimeter per second. Did that make sense? So what the system may, yes, okay, tell you here is that, okay, yes, the blood moves at a speed of 1 centimeter per second. Did that make sense? Where here it will tell you that's okay, the blood moves at a speed of 5 centimeters per second. Because, okay, here the difference was 5 megahertz. Okay. Yeah, okay. Likewise here, it will say as, okay, the blood moves at a speed of 1 centimeter per second. And as, okay, here it has said that, okay, the blood still moves at a speed of 5 centimeters per second. Did you guys get that? Clear? Okay. Now, how did we get 1 centimeter and 1 centimeter per second? And how do we get 5 centimeter and 5 centimeters per second? Mainly because, okay, what we mainly can say here is, okay, when comparing these two here, okay, we can say, okay, that the difference between, yes, okay, the two frequencies, which were, yes, okay, the transmitted frequency, sorry, the reflected frequency and the transmitted frequency is, okay, that was less. And that's why it's okay, numerically it's okay, we can say it's okay here. the blood is moving slower. Whereas, okay, what we look at here is that, okay, yes, the difference between the two frequencies here. Which two frequencies? So yes, okay, reflected frequency and transmitted frequency was greater. And what that mainly is, okay, said, okay, here is, okay, the blood is moving faster, for instance. The same applies here. It's okay, here is going to be slower. Why? Because the difference between 19 and 20 was just 1 megahertz. Right? Okay. Where here you can say, it's okay, here it's going to just, okay, be moving faster. Why? Because the difference between 15 and 20 was greater. Did you guys get that? So the numerical difference between the two frequencies gives you the speed. Please note it. The numerical difference between the two frequencies gives you the speed. The numerical difference between the two frequencies, what does that give you? The speed. What was the numerical difference here? In A, 1. What was the numerical difference here in B? 5. Okay. Likewise here, so okay, in C, the numerical difference between the two frequencies was still just 1. In D, yes, okay, the numerical difference between the two frequencies was still high, which was 5. Did that make sense? Whereas here, we said, well, okay, yes, this was positive Doppler shift. This was positive Doppler shift. What does this positive Doppler shift mean? That, okay, yes, the blood is moving towards the transducer at a speed of 1 centimeter per second. Whereas here is, okay, it was still moving towards the transducer just at a greater speed, 5 centimeters per second. Likewise here, we say, well, okay, yes, the blood was moving. It was a negative Doppler shift. Okay, but it was moving as, okay, at a speed of 1 centimeter per second away from the transducer. Or it is moving at a speed of 5 centimeters per second away from the transducer. Okay. Or, my dear guys, if we just, okay, just compare the positive slow and the negative slow. Well, okay, as far as you look at the speed, it's the same. 1 centimeter per second, 1 centimeter per second. Okay, how did we get that? Mainly as, okay, due to as, okay, the numerical difference between the two frequencies. Which we here is, okay, just said, okay, was 1 megahertz. And we just says, okay, for each difference of 1 megahertz, that's going to mean that the blood moves at a speed of 1 centimeter per second. So what does the positive Doppler shift means? Well, it just says, well, okay, it moves, or that's okay, positive Doppler shift of 1 centimeter per second. And it's okay, negative Doppler shift of 1 centimeter per second. The positive and negative just okay tells you the, as mean that's okay, just going to be as okay, the direction. Clear? Okay. So approaching at 1 centimeter per second, leaving at a speed of 1 centimeter per second. Approaching at a speed of 5 centimeters per second and leaving at a speed of 5 centimeters per second. So the plus and minus Doppler shifts only, yes, okay, are there to, yes, okay, give you the direction along with the speed, which was centimeters per second. And what did we say that speed with direction indicates? What is a speed with direction called?
Velocity.
Velocity. Clear? Okay. So you can drive from, yes, okay, from Connecticut to New York. Okay, let's just say that, okay, the transducer is at New York. You are the reflector. Now you're driving towards New York at 5 miles per hour or 1 mile per hour. They were both positives, but in one case, it's okay, when you drive 1 mile per hour, that's a low speed. 5 miles per hour is a fast speed. But since you say, okay, we're traveling towards New York where the transducer is, that becomes positive. Because you're traveling towards the transducer. The same as, okay, if you come from New York where the transducer is, let's say it's okay, back to Connecticut. You is okay, moving away from the transducer is okay, traveling from away from New York will be a negative Doppler shift. But you can travel fast or you can travel slow. How will the system determine whether you're traveling fast or slow? Is going to be as okay due to the numerical difference between the two frequencies. How big is the difference between the frequencies? Which frequency is the transmitted versus the reflected? Clear? Did that make sense? Now it's all just a matter of, okay, which of these two frequencies here is greater and which is lesser. That will determine whether you have a positive Doppler shift or a negative Doppler shift. Whereas the numerical difference between the frequencies will determine the Doppler shift. Okay, by you traveling at a speed of 1 centimeter or miles per hour towards New York, you travel at the same speed, even if you're traveling away from New York at 1 mile per hour. Clear? Okay, so the speed was the same, there was just a direction that was changed. Did that make sense? So, but in both cases, okay, it's going to be okay, plus 1 mile per hour and minus 1 mile per hour. So what the plus and minus mean is, okay, in the case is the direction. Did you guys get that? Okay, guys, and for now, what we mean by positive is travels towards the transducer. What do we mean by negative? Travels away from the transducer. Okay, why do we do that? Mainly because, okay, mathematically, yes, okay, we'll need to, yes, okay, calculate it in this way here. Does anybody have any questions? No questions?
No.
Okay, guys. Any word of wisdom? So nobody have any questions? Anything anybody wants to contribute? Okay, so what your system will be doing is, well, okay, yes, it will receive a different frequency from what it transmitted. Right, okay. And based on that, it will say, well, okay, this is how fast or slow the red blood cell is moving. That's going to give you as, okay, the numerical value of speed. Whereas plus and minus is just, okay, as directional. I mean, it's okay, just have a directional significance. Okay. So there's nothing wrong and say as, okay, negative Doppler shift of 5 centimeters per second. Nothing wrong in that. It's not necessarily a positive Doppler shift of 5 centimeters per second is good. Clear? Okay. So the positive and negative just tells you the direction. Okay, it's the actual numerical speed that, okay, yes, may play a difference. Fast and slow. Any questions? Okay, guys, so this was your Doppler 101. Let's say as, okay, the first step. And no, just take, okay, as a short while, okay, yes, break. Should we say you guys can get up to 20 minutes? Chew on, yes, okay, what you just committed yourself to? No. Okay. And Marie, yes, okay, the first, yes, okay. It's quite some page. 1, 2, 3 pages. And when we come back, yes, okay, we will look at a fellow that we will call the Doppler equation. Okay. Okay, I can already see somebody, yes, okay, giving me a nervous smile. Now, okay, guys, necessarily not an equation that you guys have to remember by heart. Okay, so relief. Well, okay, but yes, okay, some of the relationships are going to be important. Okay. Okay, guys, so I see you guys at say 10:55. Any questions? As far as what we have done about Doppler shift so far? Okay. So just remember Doppler shift, also known as Doppler frequency, is just going to be the difference between the reflected frequency and the transmitted frequency. Okay. That numerical difference will give you the speed. The frequency is just going to be translated, converted into speed. Clear? Okay. Whereas the positive versus negative mainly is, okay, just indicate the direction. Clear? Okay. Where your Doppler shift actually becomes or it gives you, yes, okay, not just the speed, but the velocity of blood flowing at such as a speed in this direction or flowing at the same speed in this direction. Did that make any sense? Okay. And how do we get it? We subtracted the reflected frequency from the transmitted frequency. If your reflected frequency is greater than the transmitted frequency, you get a positive Doppler shift. If the reflected frequency is lesser than the transmitted frequency, you get a negative Doppler shift. Clear? Okay. That was pretty much okay as where I left you guys earlier. But, okay, guys. Sorry. There was something that I left out here. Because let's say that, okay, yes, our transmitted frequency was 20 megahertz. So what would be the case if, yes, okay, your reflector frequency also was 20 megahertz? Where we could say, yes, okay, both of these frequencies, yes, okay, will not be greater or smaller, but they will actually be equal. Now that's going to be the same that we will say, yes, okay, that we will not have a positive or negative Doppler shift. And as a matter of fact, it's okay, when you subtract 20 from 20, what are you getting? 0. Is that clear? So that will be, yes, okay, what we will refer to as a 0 Doppler shift. Now, two scenarios where you may get a 0 Doppler shift. One is if you have a bye-bye to the patient. He or she is long gone. At least it's okay, there's no flow of blood. Clear? Okay, then you should start getting worried. Okay, but that's okay. Would we be able to get a 0 Doppler shift on an alive patient where the heart is still pumping blood? Yes. So some of those things, yes, okay, that's what we may come across as okay when we go over as okay or next topic, which is going to be as okay the Doppler equation. Right? Okay. So, but please keep in mind now, yes, okay, that if your reflected frequency equals that of your transmitted frequency, in that instance, that's okay, you will have a 0 Doppler shift. Okay. Or a 0 Doppler frequency. Is that clear? Okay, guys. Now, what I said earlier, so yes, okay, guys, if you got this one here, that's okay. You somehow, that's okay, got a little bit, okay, as at least some essence of, okay, what it means to be a, Doppler and Doppler shifts. Okay. Please don't come back tomorrow or it's okay at any other time and say, Mike, 1 megahertz is not equal to 1 centimeter per second. I just use this to, I mean, that's okay. Just make you guys understand it, okay? Okay, guys, Doppler equation. Right? Now we make this, okay, call it a Doppler equation. And as I said before, it's okay, not really an equation that you guys will have to remember. But at least it's okay to, it's okay, you at least be, it's okay. Required to, it's okay, remember the relationships. So this is mainly as okay, just the way at which yes, okay, the way the system is going to be able to, yes, okay, you can say, calculate or determine your Doppler shift, which we mean, yes, okay, just earlier said was your Doppler frequency. Did you guys get that? Yeah, okay. And what was it that this basically was? That's okay, just the difference between the reflected frequency and the transmitted frequency or the transducer's frequency. So what we're going to have here is 2. Now, guys, the reason that it's okay they use the value 2 here is because okay, your Doppler shift frequencies actually is okay is calculated by using 2 frequencies. Is that clear?
Yep.
Good. Now, the next thing that we will see is going to be the velocity of blood. Now, of course, okay, since blood is going to be flowing, right? Okay. Are moving or flowing at a certain speed in a certain direction. So we can make this, okay, that here is, okay, this velocity, as we already said, was going to be depending on 2 factors. First was going to be the speed. The second was going to be the direction. But now it's okay, what did we refer the direction to as? Towards or away from the transducer. Okay, now as far as the speed was concerned, because yes, okay, we could have a high speed. That mainly because, okay, because we might have had, okay, as a high velocity of blood. Or we could have a low speed. Mainly because, okay, we had a low speed or velocity of foot blood. Okay, where the other factor in velocity was just going to be the direction, which mainly is okay, give us values, which could either be positive. And what did we mean by a positive direction? Towards the transducer. The other was negative, and what did that mean? Away from transducer. Right, okay. But what we mainly can see is, okay, from this equation here is that we had a low Doppler shift, or sorry, a low speed of the blood. The blood was flowing at a low speed. All dependent upon us, okay, whether that was towards or away from the transducer, I was going to give it a positive or negative. But due to that low speed, yes, okay, we will have a low Doppler shift. Did you guys get that?
Yes.
Right, okay. Well, okay, on the other hand, if the blood was flowing at a great speed, Grade could be either be as okay, grade positive or grade negative, because the negative and positive will just mean as okay, determined upon the direction. But if the blood was flowing fast, which will mean is okay, mean at a high speed, that will give us okay as a high velocity. And due to that high velocity, is okay, we will have a great Doppler shift. So what did we get out from this equation here? Or what did we get out from this? We could mainly say as okay, that Doppler shift is directly proportional to velocity of blood. Yeah, okay. Okay. Which practically is okay. We could just say as okay, well, just I mean the same, okay, that it will have be directly proportional to the speed of blood. Because as far okay as the velocity is concerned, yes, okay, the positive and negative mean yes, okay, are just terms of direction. Or what I pretty much okay is just proved on my previous slide that you see here. The case is just okay where we had a low speed. Whether it was positive, whether it was negative, mainly gave us okay as a low Doppler shift frequency. Compared to yes, okay, where we had a great speed, positive or negative, was mainly because okay, we had a great Doppler shift. Did you guys get that?
Yeah.
Good. So what did we get from that? That velocity is directly proportional to the Doppler shift or Doppler frequency. Clear? What did that Doppler shift or Doppler frequency mean? That the difference in the two frequencies. Which frequencies? The transmitted versus the transmitted frequency versus the reflected frequency. Did you guys get that? Okay. Now, guys, as far as these frequencies are as okay, Doppler shifts or velocities as okay, here can be recorded. Do you guys mind if I go to another slide for a sec?
No.
Good. Now we can have yes, okay, spectral. Okay, as I say, it's okay. This boring fellow here is okay. Is obvious. Okay, just say would be yes, okay. A spectral Doppler. The remaining can say it's okay that our velocities are going to be as okay expressed in terms of okay being displayed as a bigger or smaller graph. Okay. Now, some system, yes, okay, on one side, yes, okay, they may give you, yes, okay, values in hertz. Whereas on the other side, yes, okay, they may give you, yes, okay, values of, yes, okay, centimeters per second. Where you mainly will say, yes, okay, here we can just, okay, now this, as I showed you guys the other day, let's just use this computer. This line here is okay, that was what we call the baseline. Right, okay. Okay, and what was it that this baseline here is okay, mainly would indicate was a zero Doppler shift. And likewise over here, so okay, zero Doppler shift, or we can say it's okay, 0 centimeters per second, which may mean that okay, the blood is not moving, or we are carrying no Doppler shift. Okay, whereas in most instances, okay, now just as okay as a regular graph. You could say, okay, this may be as okay, just okay as going by 10 hertz. Which VH on the other side will say, it's okay, may just go by 10 centimeters per second. So we can say, it's okay, if we for instance, okay, had a blood flow at a low speed, that was going to give you, as okay, a low Doppler shift frequency. Let's say 20 hertz of a Doppler frequency. Okay. Now, why would this be as okay positive? Because mainly as okay, we said that okay, as the reflector frequency was greater than the transmitted frequency. But where we, on the other hand, is okay, where we follow this graph, because it's okay, that 20 hertz will lead to is okay, or be translated into is okay, a positive Doppler shift of 20 centimeters per second. Did you guys get that? Whereas, okay, as on the other hand, if we had a great Doppler shift, let's say something like this, where the difference between yes, okay, or two frequencies was 50 centimeter, 50 hertz, for instance. Okay, but where we stay as okay, say okay, as the reflector frequency is still greater than the transmitter frequency, that makes it positive. But here's okay, we have a greater difference between these two. Actually, it's okay because it's okay different from 50 hertz. But this graph is okay if we look at it. Okay, or could have been it's okay demonstrated. It's okay, maybe it's okay. Let's do it this way. And we follow this line, and okay, yes, it's going to say okay, yes, it follows at a flow of. It flows at a speed of 50 centimeters per second. Clear? Okay, so where we could mainly say is okay, that in this case, yes, okay, this orange one here is okay, sorry. That was going to be as okay, a great positive Doppler shift. Because of a great frequency difference between these two frequencies here, mainly as okay, we will do as okay, the blood flowing at a greater speed. Or on the other hand, yes, okay, the yellow was going to be as okay, a low positive Doppler shift. Why? Because it's okay, we had a lower difference between, yes, okay, the two frequency, the transmitted and reflected. Okay. Which mainly, yes, okay, is going to be translated into, yes, okay, I mean, yes, okay, be due to, yes, okay, the blood flowing at a lower speed. Okay, now the same, yes, okay, will apply, yes, okay, if you go on the other side. Now, anything is okay below the 0 line or the baseline, unless and until, yes, okay, your graph isn't inverted or flipped upside down. All these values from 0 and below are going to be negative. All these values here are going to be positive. So we can just go and say it's okay, the same. -10, -20, -30, -40. And for instance, that's okay, -50. Okay. Or that's okay. -10 centimeters per second, -20 centimeters per second, -30 centimeters per second, -40 centimeters per second, or -50 centimeters per second. That is okay, of course. If we had a lesser difference between, yes, okay, your reflected and transmitted frequency. Okay. That was going to be, yes, okay, a lesser Doppler shift compared to, yes, okay, we had a greater difference between the two frequencies. That was going to be, yes, okay, a greater Doppler shift. But they're both going to be negative Doppler shifts. Why? But that's okay, they're displaying negative Doppler shifts on your system. Okay. Now, how does the system is okay determine that? That's mainly because that we can say, okay, that okay, yes, in both these instances, okay, that your reflected frequency was that the reflected frequency is okay was lesser than the transmitted frequency. Okay. That makes them both negative Doppler shifts. Right, okay. Whereas here, this lesser is a lesser difference. Here, greater is going to be okay, greater difference between the two frequencies, which we will try to translate into is okay. A small Doppler shift frequency, which actually is okay, will be recorded as a lower speed, or a greater Doppler shift, which is going to be okay, be a greater speed, but they will both be negatives. So this here where it's okay, still be as okay your positive Doppler shifts, and these here is okay will be your negative Doppler shifts. Unless and until yes, okay, the system or yes, okay, the spectral Doppler is not inverted. Then negative is going to become positive, and positive is going to become negative. Did you guys get that? So what we made is okay, just see in this case is okay, displayed along the y-axis. on the spectral Doppler. Is going to be as okay either the Doppler shift, which also is okay on the other side, can be as okay the velocity. Whereas, okay, as what you see along the x-axis in a spectral Doppler is going to be time. So guys, if you yes, okay, follow a spectral Doppler like this, and where you mean is okay, let us say that in this case, if we have positive Doppler shift. Something like this. This may be as okay the last reading that you took. This before that, this before that, this before that, this before that. Okay. It says, okay, this was the 0 point. This is when you start. Okay, okay, it says, okay, the longer, yes, okay, the time for which you record is okay. The longer and longer and longer is it that your graph is going to be horizontally. Did you guys get that? Did you guys get that?
Yeah.
Now, whereas if we looked at a color map or a color Doppler, well, the black in the middle is always going to be as okay as 0 Doppler shift. Now, guys, please, as okay, if this map here hasn't been inverted, we can say it's okay. And I may go with, let's say it's okay, this. And I say it's okay, this. And we can say, let's just go with this, and then you can say it's okay. Let's just go with this. Clear, okay. Now, since this is not inverted, we can mean it's okay, all these colors, yes, okay, what would they represent? Positive Doppler shifts. Whereas, okay, yes, we can go on the other hand and we can say it's okay. This and this and this, and let's just see, yes, okay, lastly this. We're all being yes, okay, negative Doppler shifts. Okay, now as I say, it's okay, color Doppler, yes, okay, so that's going to be that, okay, as your blood vessel, for instance. Now maybe it's okay, filled up with any color. Let's just say that, okay, yes, it's red. Now in this instance, is okay, what is it that the red will tell us? There was a positive Doppler shift. Right? Okay. Now, since we see red, that's okay. There may be a number up here. Let's say it's okay. 40 centimeters per second. Did you guys get that? So since we see red here, that mainly means, okay, that this red here mainly represents blood that flowed at speed of 40 centimeters per second. Let's say that, okay, as in the midst of all this, that's okay, that maybe blood that flows at a slower speed, let's say it's okay. Some .30 centimeters per second. Okay. That's okay in the 30s. From 29 to 39 for instance. Okay. And like, well, okay, yes, something is okay. Let's say even slower. So the colors mainly is okay, will represent different speeds, but we can say, okay, we had seen any color on the positive side is okay, mainly is okay, filling up the blood vessel. That mainly meant that, okay, we, in this case, it will have had a positive Doppler shift. Whereas, okay, yes, if that same blood vessel, yes, okay, we had showed us colors on the negative side. What is this? Okay, what would that have meant? That mainly had meant that we have had a negative Doppler shift. Slower, faster, even faster, very fast. Or fast as okay, the speed limit that we were able to measure it. Because even as okay on the spectrum, as okay, I kept the speed of okay, max positive 50 centimeters per second, max negative 50 centimeters per second. These values here could be increased. This maximum value or this maximum value here could be increased. So could this maximum value or this maximum value here also be increased by increasing the PRF. Or something that we'll talk more about is okay when we get to the aliasing. Okay. But the greater the speed difference, the greater is going to be as okay your Doppler shift. On a spectral Doppler, that greater Doppler shift is going to okay be a greater spike, which will be translated into as okay faster speed, lesser Doppler, lesser difference, lesser Doppler shift, slower speed. Did you guys get that?
Yep.
Okay. Or is it just flying on top of your heads like aliasing?
No, I think it makes sense.
Okay, for you it makes sense. What about the other girls and what about the gentlemen?
Makes sense.
Yeah,
Okay, well that's good. At least Doppler makes sense. Okay. Let's see for how long that lasts. Oops. Okay, guys. So again, yes, okay, as I said, yes, okay, you don't necessarily have to remember the long, horrible equation here. Clear, okay? The previous equation, yes, okay, you have to remember. What one? That's okay, reflected frequency subtracted from transmitted frequency. That one you'll need to remember. Clear? Okay. But this one here, and you're okay, not necessarily. But the relationships are important. So what was the next component? What was the next thing that we had in this equation here? Oh. We mainly is okay, go say it's okay, that was going to be the transducer's frequency. Did you guys get that?
Yep.
Good. Now, what did we mean by the transducer's frequency? The frequency of the transducer, right? Okay. Which frequency is that referring to? The main frequency. Okay. The main frequency of your transducer. Is that clear?
Yeah.
Okay. And ladies and the gentlemen, yes, okay. Since you just see this here as okay as being a numerator of your equation, what can we mainly say it's going to be? It's also going to be as okay directly proportional to your Doppler shift. Now we can just put it this way and say it's okay. If we had a transducer with a low frequency, let's say it's okay, 5 megahertz, which we say is okay, it was going to be a low frequency transducer. That will mainly cause that, okay, yes, your Doppler shift will also be low. Okay, that's the wrong color. Sorry. Yeah. Whereas, okay, yes. On the other hand, if we used, now please keep in mind, guys, if you use the high frequency transducer, let's say it's okay, 10 megahertz transducer. That was going to cause, okay, the Doppler shift to be greater. Now, please keep in mind here that that's going to be as okay, irrespective. Or even as okay, if the blood, for instance, okay, was flowing at the same speed or at the same velocity. Did you guys get that?
Yep.
Okay. So even, yes, okay, if your blood was flowing at a speed that we, for instance, okay, record as, this is okay, 20 centimeters per second. Right, okay. If the blood, for instance, okay, was flowing at a speed of 20 centimeters per second. But we can say it's okay. Let's say, okay, that was just okay, recorded okay, when we use as okay a low frequency transducer. This velocity of blood here actually is okay, will still give us okay as a low Doppler shift. Whereas okay, as if the same blood flowing at the same speed was recorded using a high frequency transducer, we will get a great Doppler shift. Is that clear?
Yeah.
Okay, so your Doppler shift will increase. The velocity still remains the same. Clear? Okay. So that's okay. What you will see is okay, your exercise questions that they will be asking you is okay, which has the greatest velocity, which has the greatest Doppler shift. Now, please keep in mind, guys, okay, you can change your Doppler shift. The Doppler shift is something that you can change. How? One of the ways we just got here, by changing the frequency of your transducer or using a transducer with a different frequency. Did that make sense? You can actually increase your Doppler shift or decrease your Doppler shift. So the only thing that you need to remember is, okay, yes, what is the relationship between the Doppler shift and the transducer's frequency here? Yeah, okay. And they are going to be directly related. Okay. Did you guys get that? So when you use a transducer with a greater frequency, what is it you will be getting? A greater Doppler shift. Did you get that? Whereas, okay, if you are using a transducer, or if you are using a transducer with a lower frequency, what will you get? A lower Doppler shift. Although, yes, okay, the blood is flowing at a constant speed. Okay? There's nothing that, okay, as you can do to just, okay, increase the speed of the blood flow on the patient. You can, but it's not recommended. You may say, oops. Okay, and that's going to increase the speed of the patient's blood flow. Right? Just if I just say, oops. I just received an email from Lauren. And what she says is that we have to just, okay, move your final date up. Because the campus is going to be closed after, yes, okay, March 12th. So your final year guides are going to be on March 11th.
Like our final?
Final. Now, if I took your Doppler right now, your the velocity of your blood would have gone up quite a few miles, right? Okay, no. Okay, great. That's why I say it's okay. You can increase the speed of the patient's blood flow, but that is not recommended. Okay? You might give them a heart attack right there.
Mike, are you joking?
Yeah, no. It was a practical joke. Let me put it that way. No, I didn't receive anything yet. But what happened to you, dear? Didn't your heart go like, okay, something like that? Yeah, okay. So that's why I say it's okay. You can increase the velocity, but it's okay. That is not recommended. Okay. Okay. But even it's okay if the blood was flowing at the same speed. You can still increase or decrease your Doppler shift. And how would that be done? By using a transducer with a greater frequency or a transducer with a lower frequency. So the lower frequency transducer is going to give you a lower Doppler shift. The greater frequency transducer is going to give you a greater Doppler shift. Clear? Okay. That good may be good. You may in some cases find that, okay, yes, that good may be good. Why? Because, okay, in some instances, okay, the blood may be flowing so slow that you will have a hard time to, let's say, it's okay, get a Doppler shift recording. Clear? Okay. So what can you do to, yes, okay, increase the difference between the reflected and transmitted frequency? Increase your transducer's frequency. And that will go as going to give you, yes, okay, equal increase in the reflected frequency, or equal difference in the reflected versus transmitted frequency, and you will have a greater Doppler shift. Where you actually is okay, maybe able to is okay record a mention worthy as okay Doppler shift. Okay. But this relationship here is okay, it's going to be a fellow that you really is okay will make handy when we talk about aliasing. So just remember this much for now, guys. Greater transducer frequency, greater Doppler shift. Lower transducer's frequency, lower Doppler shift. Clear? Okay. And how do we get that? Mainly as okay, just by looking at the equation and saying, well, the transducer's frequency is directly proportional to the Doppler shift. So even as okay, if the speed or the velocity of the blood was the same, whereas okay, if we used a low frequency transducer, that would give us a low Doppler shift. If on the same patient, yes, okay, we used a high frequency transducer, so we'll get a high Doppler shift. Did that make sense? Okay, guys. The next thing. Now we're probably going to take that one after the lunch break. Okay. And that's going to be as okay, Warrior says okay, will be as okay, the cosine theta. We will check that off the lunch break. What you see as okay as your denominator is the propagation speed. And here is okay, guys. This means okay, just the propagation speed of sound. But that's not really as okay something that is okay is being discussed, so we're not going to be bothering ourselves about it. Any questions so far?
No.
Good, guys. So before talking about the cosine theta, you guys can go, you can have your lunch. Clear? Okay, and if you get time, please just okay, go to chapter number 6 and look at the angles. Normal incidence versus not normal incidence. Clear. Now, do you guys recall what I said back then, 13 chapters ago? Why did we call a 90-degree angle a normal incidence? Because that was the ideal angle to get a what? To get an image, right? Good. Now, guys, what I said, briefly mentioned back then, but we'll say now, is that the goal of a Doppler is not to create an image. The goal of your Doppler is primarily to measure the speed, if not the velocity of blood. Did that make sense? Clear, okay. So what back then was normal is now going to become abnormal. And what back then was abnormal is now going to become normal. That's all I can say. Okay, guys. Take your lunch break and I will see you back at 12:50. Okay. And don't worry about your chest has not been moved up. Any questions so far about the Doppler equation?
Not yet.
Not yet. Okay, good. Now let's just look at this last fellow here. Good. Cosine theta. Okay. Now, guys, oops. This cosine theta is actually going to be, so okay, we can say the cosine theta value of the angle. And now this angle here is going to be between two things. Between what we will say be the beam of ultrasound and direction of blood flow. Is that clear?
Yep.
Okay. So what we actually mean by the theta or cosine theta is that, if you put it this way, saying that, okay, yes, the blood was flowing in this direction. Okay. And your beam, for instance, was like this. Now what we see here is, okay, is that there is going to be an angle between these two here. The angle that we have here is 90 degrees. Did that make sense?
Yep.
Good. Now, this 90 degree here is okay, has a cosine theta value. So the cosine theta value of 90 degrees is, for instance, 0. Did you guys get that? Now, if we just look at that, oops, if you say that was the case, here you will enter 0. And that's why I said, yes, okay, you can still get, yes, okay, a 0 Doppler shift, even though, yes, okay, the blood is flowing at a certain speed. Okay, you have a frequency or you have a transducer with a certain frequency. Clear? Okay. So all that is going to be as, okay, multiplied by 0. Even as, okay, when you say, so even if you double all this, and you end up multiplying it by 0, anything multiplied by 0 equals 0. You guys get that? So it's not going to be that you multiply by 90. No. 90 degrees is the angle. That 90-degree angle has its own cosine theta value, which in this instance, yes, okay, it's going to be 0. Did you guys get that? Okay, but what is going to be the cosine theta value that we were looking at is going to be talk about is going to be, okay, the cosine theta value of the angle between the ultrasound beam and the direction of the blood flow. Did you guys get that? Yes, guys.
Yes.
Yeah.
Now, please keep in mind, guys, we are not having a geometry measure. Okay, okay. If your subject was geometry, and we can say, okay, the only thing that we'll be dealing with was this angle, that angle, beep, beep, boop, boop. Then it might have been required that you know as okay, the cosine theta value of all your angles from 0 to 360. Yeah. Okay, but that's not what we have here. Okay. The major thing is, let me see if I can break this down. Now, guys, please take your eyes off your books for a little time and try to pay a little attention here. So, guys, if we, for instance, said that, okay, yes, here, if this was our blood vessel, is that clear? That's our blood vessel. And if we just, for instance, say, it's okay, let's just say, okay, what color is it? That's okay, the direction of the blood flow. Okay, good. So if we just said, okay, yes, in our instance here, if the blood was flowing in this direction here. Did that make sense?
Yes.
Now, we also already said that, well, okay, yes, if this was the direction, and yes, okay, this was the direction of the beam, yes, okay, this here will make, okay, yes, a 90-degree angle. Okay, this was a 90-degree angle, and we already said that, okay, at this 90-degree angle here, it's okay, at a cosine theta value, which was 0. Okay. I'll just keep my try. Okay, so okay, to assume that okay, yes, this here is okay, was your transducer. Now, guys, let's just start from here. Now, if this here is okay, was your transducer, it will be sending out a beam. Okay. Now, what we actually is okay, or what we actually can say is okay that here is okay the angle between the beam and the blood flow, they will form a 0-degree angle. Now, guys, the cosine theta value of 0 degrees equals 1. Is that clear? To be more clear about it, okay, that's going to be +1. Now we may go and say, yes, okay, where if we scan from angle like this, now this is going to be as okay, presumably as okay, 30-degree. So if we scan from, let's say, it's okay, this angle here, we can mainly say it's okay that the angle is okay produced between the beam Yes, okay, the blood flow here. This will be as okay 30 degrees. Now, this 30 degree is okay has a cosine theta value that is going to be equal to 0.85. So 875. Or to be more accurately saying plus. Whereas, okay, yes, if we say that, okay, if we were scanning from an angle like this, which will say is, okay, we're having is, okay, is a 60-degree angle. This 60-degree angle here is, okay, has a cosine theta value that is equal to 0.5, or more accurately is, okay, plus 0.5. So roughly saying is, okay, this could be a 60-degree angle. Did you guys get that?
Yeah.
Good. Okay. Now, mainly as okay in this instance here as okay, you know, since you can make this okay as the blood was flowing in this direction here. Where it was from a zero, okay, whether we had a 0-degree angle, whether we had a 30-degree angle, whether we have a 60-degree angle, we can still say that, okay, yes, the blood flows in a direction which is towards the transducer. Now, the towards the transducer mainly as okay causes that these were all positives, right? Okay, clear?
Yep.
Good. Okay. Whereas the actual value, oh, we come to that later. Okay. Whereas, okay, here is okay, formed a 0-degree angle. Here forms a 30-degree angle. Here forms a 60-degree angle. And each of these angles just okay had their own cosine theta values. Whereas, guys, okay, and it's going to be as okay, these cosine theta values that we will be ending up putting in these equations here. Okay, now guys, as I said earlier, it's okay, you're not going to be asked to calculate your Doppler shifts using this equation here, but the relationships are important. Okay, so now on the other hand, guys, when we go on this side here, now that's okay. When you add a 30 degree onto 90, what do you get? You can mainly say, okay, this is going to be an angle of 120 degrees. Now, my dear guys, the cosine theta value of your 120 degrees is equal to 0.5 negative. And why is that? Mainly because, okay, we can mainly say that, okay, yes, the angle between the beam and the blood flow. Yes, okay, was 120 degrees. Where you can mainly says, okay, until 90 or 89 degrees, it was positive. Then at 90 became 0. And then it's okay, it's going to go on negative. Whereas, okay, yes, if you go with another 30 degrees on to 120, you can say it's okay. Oh, this may become that okay. This here. Now, this was supposed to have been, it's okay, yes, we can say it's okay, 150 degrees. Now, 150 degrees, what does that have? It also has a cosine theta value. And the cosine theta value of 150 degrees is going to be 0.87, or more accurately saying, negative. Whereas if you go here, if you see it's okay that this was the way in which, yes, okay, our beam was being transmitted. Now we can mainly say, okay, it's going to, yes, okay, be flowing completely at the opposite direction from your transducer. So this is going to be, yes, okay, totally off 180 degrees. Now this 180 degrees also has its own cosine theta value. And that is equal to 1. Or more accurately speaking, -1. Did you guys get that?
Yeah.
Clear? Okay. So what was all this about? Mainly saying, yes, okay, the angle between the blood flow, or the direction of the blood flow, and the sound beam. Okay. Those angles have their own cosine theta values. And it was those cosine theta values that we put into the equations. Okay, or where we can say, okay, any angle that was between 0 degrees to 89 degrees were positives. Anything from 91 to 180 were negatives. Okay. Because, okay, so it says, okay, even if it's okay, just draw, for instance, okay, angle here is okay, that's going to become, yes, okay, from here to here, yes, okay, this is roughly around F20. And here is okay, 180. Okay, 180 because mainly it's okay in the opposite direction of your transducer. Okay, now had it, let's see, it's okay, Kurbia says okay, had it been, it's okay, the transducers in the same locations as we had here. But the blood, for instance, okay, had been flowing in this direction. And okay, as if you had been scanning from here, it's okay, this would have been okay as at a 100-degree angle. And mainly as okay, what had been having that cosine theta value of -1. This would have been as okay, the 150-degree angle. Okay, which means okay, this would have had that cosine theta value of minus 0.87. This would have been as okay at 120 degrees. Mainly as okay, just then having as okay that cosine theta value of minus 0.5. Well, 90 will still be 90. Did that make sense? But then now, yes, okay, these here is okay, will become positive. So yes, okay, this will have been a 60-degree angle with the cosine value of plus 0.5. 30-degree angle with a cosine theta value of 0.87, or more accurately, that's okay, plus 0.87. And this one here would have been 0 degrees, which would have been having cosine theta value of plus 1. Okay. So here is okay. This would have been it. This would have been it. Why not do this? Did you guys get that?
Yes.
Good. So based on our formula, our Doppler equation, now we can mainly say that okay, yes. Now here this is mainly is okay the whole point. So we says okay, Doppler shift was equal to 2 multiplied by the velocity of blood multiplied by is okay the transducer's frequency multiplied by is okay cosine theta value. Okay, now guys, the important point is that it is at angles of 0 degrees. What do we mean by an angle of 0 degrees? For instance, okay, if the blood was flowing this way and we were scanning from here. Yeah. Okay. And 180 degrees. Now, what does it mean to be as okay 180 degrees? We could say as okay, just like yes. If we were scanning from here, and let's say it's okay, the blood was flowing in this direction here. Okay, but it's only going to be at these two angles here that the measured velocity equals the actual velocity. Why? Because it mainly was at these two angles here, whereas the cosine theta value was 1. Did you guys get that?
Yeah.
So the whole equation would have been multiplied by 1, right? Okay. Where you, for instance, say what about if you go to, for instance, the angle of 60 degrees, and opposite of 60 degrees would have been 120 degrees, right? Now, these two angles, what did they respectively have? Their cosine theta values were plus 0.5. And the cosine theta value of this one here was minus 0.5. Clear? Okay. So yes, if you, for instance, measuring at an angle of 60 degrees or 120 degrees. Okay. Now what the 60 degrees will give us, was mainly just half, or we can say that the measured velocity actually is just going to be half the actual velocity. So for negative, or so for 120 degrees. Okay. Now the only difference between the 60 and 120 was that as 60 degrees, that was going to give you a positive Doppler shift. The 120 degrees was going to give you the negative Doppler shift. But the velocity that we will be measuring was going to be half the actual velocity. Yeah, okay, so all this, math here would at the end mainly just be multiplied by 0.5, which makes it half. Okay. The positive, it could either be as positive or negative. Likewise for here, it could have been positive or negative. The positive or negative mainly is just indicates the directions of the beam related to the direction of the blood flow. Did you guys get that? Whereas on the last but not the least, we can say, what if we went for things such as a 30-degree angle or a 50-degree angle? Now both of these had cosine theta values of 0.87 and 0.87. Those still greater than half, but yes, still less than 1. Is that clear? So the main point, guys, is that only at angles of 0 degrees and 180 degrees is it that the measured velocity is the actual velocity. Clear? Or no matter what, at all angles. Measure velocity is equal to, we can say it's okay, the true velocity times your cosine theta value. Now what we mean is, okay, meant here by the true velocity is what we is, okay, in our Doppler equation said, well, okay, the velocity of blood is due here. So only where the angle was 0 degrees or 180 degrees, this whole equation is okay. Well, ultimately, it's okay. We multiply by 1. And we can say that, okay, yes, the measured velocity equals the true velocity. Or we say it's okay at 60 degrees or 120 degrees, measured velocity is going to be equal to half the actual velocity. Now, some of you may say, so what about the cosine theta value of 45 degrees? Do we need to remember that one? No. Yeah. Do you necessarily need to remember, yes, okay, all these values here? Not really. Okay. But it's made as, okay, just 3 numbers. 1 degree and 0 degrees and 180 degrees is cosine theta value 1. 30 degrees and 150 degrees is 0.87. 60 degrees and 120 degrees is 0.5 plus minus. And 90 degrees is 0. So yes, okay, even that's why I said, even though, yes, okay, blood was flowing, even though blood was flowing, but if your box was at 90 degrees, you will not get a Doppler shift. Yeah, okay. So one of the optimizing that we will be doing in chapter 20 is how to get a Doppler shift. Although it's okay, we see the blood vessel right there. We also made sure that the patient is alive. Right, okay, okay. Okay. And but we still don't see a Doppler shift. Why is that? Mainly because it's okay that our box is not steered the right way. Did that make any sense? So if you were looking straight at, okay, the blood just was flowing like this, then okay, yes, that was a 90-degree angle. And you would not have a Doppler shift. So a lot of these things here is, okay, guys, are going to be brought up again and again and again, whether it is in this chapter, whether it is in the next chapter. Now, guys, does anybody have any questions? So if it says 90 degrees, that's okay. You don't multiply that whole equation by 90. No, that 90 degree has a cosine theta value, 0. 60 degrees or 120 degrees, both are as okay, either 30 less than 90 or 30 greater than 90, right? That's the cheat. Just remember one side and the other side is going to be positive. If the other side, the one that you remember was negative. Okay. So both 0.5, 0.5, but 60 was plus, 120 was minus. Then we go 30 and 150. Okay. Please, that's okay. It's the angle between the beam or pulse, whichever, and the direction of the blood flow. So 30 would be plus 0.87, a weird number, and 150 would be minus 0.87. And then 0 and 1, either standing right frontal. That's okay, standing, I mean, it's okay, looking at it, it's like moving straight away. Did you guys get that? Okay. But what you mainly can get by is, okay, steering your angle or your box is you can make, okay, as a positive Doppler shift become negative. And likewise, it's okay, a negative Doppler shift become positive. So how was the first day of Doppler? Yes, guys.
It's fine.
That's fine. Okay, good. Do you know that nowadays cars, even, yes, okay, have a Doppler mechanism in them? Now, I don't know what kind of car you be driving or what year or model or make. But it's okay, nowadays it's okay in the side mirrors. They have a little light that may flicker. Especially it's okay if you indicated that you want to, it's okay, make a line shift. What does that tell you? Don't make a line shift because there's a car in your blind spot, right? Do you guys know what a blind spot is? Or are you one of those who says, okay, everything on the road is in my blind spot? I don't see anything. I just go and millions, okay, just demand that people make way for me. Right? Are you one of those, Kristen? Okay, you are just nodding. Yeah, that sounds like me. No, okay. Yeah, if you are that, then you should. Then I would recommend that you drive a tank. Okay, guys. So yes, okay. Please, you will find you probably yes, okay at bottom of page 309. You find a little equation. Sorry, measure velocity. What you get from your Doppler shift equation is the product of, okay, is the true velocity, the actual velocity of the blood multiplied by the cosine theta value. Clear? Okay. So only as, okay, if you multiply something by 1, you will get the actual, yes, okay, the measure and the actual value will be true. If you measure, yes, okay, the actual velocity or any value with half, it will become half. Clear? Did that make sense? And you multiply by something that is going to be 0, yes, okay, it doesn't really matter. It will be 0. Any bigger or smaller number that you have, you multiply that by 0, it becomes 0. Where do you have a 0 Doppler shift? At a 90-degree incident angle. So what in regular diagnostic imaging was the normal incidence, right? Here is the not normal incidence, because that gives you, yes, okay, a 0 Doppler shift. Okay, guys. Now, what I would recommend you guys do, well, okay, we did a lot of pages today. Well, that's okay, guys. Okay, as I said, the Doppler equation itself is not important. The relationships are. So what do you say now? Greater the cosine theta value, greater is going to be the Doppler shift, or let's say it's okay, what we have referred to as the measured velocity. Clear? What's the greatest cosine theta value we got? 1. What gave us that? 0 degree and 180 degree. 0 degree is positive, 180 degrees negative. Clear? Now, guys, read on this, and if you have any questions, feel free to ask. If you have any questions right now, I say, Mike, do you mind explaining this one here once again? I didn't fully get it. Nope. Good. So I guess, okay, that's a good start, I guess. Was it too much? Nope. Okay. Good. So what was a Doppler frequency? You can say anything if it makes sense to anything that I've been talking about so far. Yes, okay. What would be a Doppler frequency? Oops.
The motion between the sound and the receiver. That creates a change.
Now, my dear, the motion between, yes, okay, the source and your reflector, that's going to, yes, okay, that will give you your Doppler shift. A Doppler shift was the difference between transmitter frequency and reflector frequency. Okay, so here's, okay, we have two frequencies again to deal with. Okay, transducer frequency is, okay, the good old one that we have been talking about since chapter 3. Reflector frequency now here is going to be different from, is okay, pulse to pulse to pulse to pulse. And mainly is okay, with help of those differences, it was says, okay, is it moving away? Is it moving closer? And due to, yes, okay, that changes in the difference will also help us to determine, well, okay, if it moves away or if it moves towards us, at what speed. That's why I said, yes, okay, listen to, yes, okay, or watch some of those submarine movies. Right, okay. Because, okay, you may say, okay, the more go, that's okay, there's a, well, okay, we are close to collision. Clear, okay. It may sound strange, even as, okay, aeroplanes have something like that. Planes that flies in the sky. If something is okay, is approaching it too fast, that's okay. The pilot may get, okay, as an alarm. Because it's not going to be everything that he or she may be able to see out through that small cockpit window. Right. So if you're flying like this or something is coming like this, okay, yes. On the hell would you know? But the distance is still decreasing, right? And this pilot has, okay, maybe drunk. Who knows? Now, had Titanic have had, okay, something like this, it probably wouldn't have sunk. Anybody watch the movie Titanic? Which one?
The original one.
The original one.
Yeah, the one with Leonardo DiCaprio.
Okay, that's not the original one.
There's another one.
There's probably, okay, a whole bunch of movies made about the Titanic.
You asked if anybody saw the Titanic. That's the
Okay,
Titanic.
of course, good. Okay, but there are other movies as well. Okay, so what is the pulse duration of that one?
Are you asking about the length of the movie?
Yes,
It's like 3 hours or something like that.
3 hours or something like that. Okay, now when you say length, what if I say, is okay, measure it in distance? And that would not have been a pulse duration, right? If you measure something in distance, and if that was a pulse, what did we call that? Yes, Teresa, if you measure the length of a pulse in distance, what do we call that?
Your wavelength?
What is the wavelength? Anybody?
Wavelength is the distance of one cycle.
One cycle. Good. Okay. So what would be the distance of a pulse then? Spatial pulse length, my dear. Good. How is your spatial pulse length related to your longitudinal resolution? How is the spatial pulse length related to the longitudinal resolution? Huh?
Inversely.
Inversely. Right, okay. What the hell was a longitudinal resolution?
Is that your axial?
That was your axial resolution, right? Okay. Which array transducer will have an equal lateral resolution and slice thickness? Which array transducer has an equal slice thickness and lateral resolution?
Would it be mechanical?
No.
Annular.
Annular. Lillian, my dear, the reason that the mechanical was not the answer because your mechanical is not an array transducer. You only got one focal point, right? Okay. So please, that's okay. Whenever you see or hear the word array, what directly should hit you is this is a transducer which enables us to focus at more than one point. Okay. Now, it enables you to do so. It doesn't necessarily mean that you have to. Okay. Now, your car may go up to, yes, okay, 320 miles an hour. Okay. Have you ever taken it to that speed? No? Okay. You are always the one who drives right in the middle of the highway at 55 miles per hour? Just wondering. Okay. Like, okay. So just because that's okay, something allows you to do it, it doesn't necessarily mean that you have to. Because you should know what are the plus points of, okay, yes, focus at more than one point. Okay. You will get, okay, better lateral resolutions at those points. Well, that's okay. If you are just okay trying to just okay record or scan something that is constantly moving, then okay, that probably won't be a good idea to do so. To focus at multiple points. Yeah, okay. Does that make sense? Okay. But the reason that your answer was wrong is that I said annular. Had I taken the word annular, array, sorry, The word array out of the question. Yes, okay, yours answer were correct, and so would have been catalyst. Or both of them have equal elevation and lateral resolutions because of their rounded or yes, okay, disc-shaped PCTs. Whereas in all of your other array transducers, due to yes, okay, the rectangular shapes of the PCTs, elevation or resolution is always going to be poorer than the lateral resolution because the height of the PCTs was greater than the width. What do we mean by the Curie point?
It's the highest temperature that the transducer, the crystals can reach.
Okay. They can reach a temperature beyond the Curie point.
But then they become damaged.
They'll become damaged. So we may say, okay, the Curie point or Curie temperature is mainly as okay a temperature at which piezoelectrical material undergoes polarization. And what was polarization? The process of converting or creating a piezoelectrical effect. And what was the effect? What was the piezoelectrical effect? Mainly it's okay, converting one form of energy into another. In our transducers, what was the piezoelectrical effect? Converting electrical energy into sound. That was during transmission. And converting that very same sound back into electrical energy, and that was during reception. Did you guys get that? How is depth of view related to attenuation?
Direct.
Pardon me?
Direct.
Direct. Okay. I just changed the word pathland out with depth of view because that's okay. The greater the depth of view you have, yes, okay. The greater depth of it that you go with your image. Okay. And the greater and greater and greater distance, that's okay. The sound wave will travel, the more is it that it will attenuate. Clear? Okay. And with that say, it's okay. Now, had it not been for compensation, had it not been for compensation, those reflections returning back from great depths would have been so weak that they would hardly produce any meaningful image, even though they were amplified by the as a result of amplification. Did that make sense? Okay. Now, an example that just struck my mind this morning was, and again, yes, okay, your echoes. Have you ever heard your echoes coming back? Now, two things. You say, hello, how are you? Okay. Now, the first time you hear that echo, that's going to be louder. But then it'll go, hello, how are you? Hello, how are you? Like that. It goes from louder to less loud. Clear? Okay. Now, why did you hear the first echo first? Because that was the echo that reflected back first at you. Why? Because, okay, it hit that structure that was going to produce the echo that reflect back. Now, the second echo is going to be following the first echo because it returns back to you from a farther distance. So that's why you hear it after the first. So like the first after that's okay, the third after the second, and the second or the fourth after the third, and so on. So, okay. Did that make sense? Okay. But you will hear that the first echo is loudest, followed by the second, which is less loud, and so on, so on, so on. And the reason that they get lesser and lesser and lesser and lesser in loudness is mainly because it's a lesser and lesser and lesser intensity of sound that reflects back. But the reason that they come one after another is because that they return back from greater and greater distance. So I think it's okay, that's something that may explain attenuation. So it's okay. So that's something that, okay, struck me this morning. So you guys may say, okay, what do you think about when you get up in the morning? I know. So it's okay. Let me just bring this one here on the record. Any last questions? It. Then, dear guys, let me see what is it. Financial year, okay, good. Tomorrow. Okay, guys. Want to do some. Let me see. That will not be the best. Okay, guys. Now tomorrow we will be talking about, yes, okay, transducers and Dopplers. Okay, now please make sure that you know the differences between pulsed wave transducers and continuous wave transducers. Clear? And have looked into, yes, okay, your backing material. That's all. Okay, just keep in mind, okay, as pulsed wave, that's okay. We'll be talking about things that's okay, which we previously related to, that's okay, PRP and PRF. Same things that's okay will be applied here. They'll just go under a different name. Okay, let's say it's okay, the PRF will go under a different name. Okay, guys? So indirectly, it's okay, you get a revision. have fun and okay, just try to read on your just okay Dopplers, what we did today as well. Okay, guys. Now, see you guys tomorrow, unless you are scheduled to see me later. Take care, God bless, and have fun.
Bye, see you
Bye-bye.
tomorrow.
Correct. Bye-bye.
See you tomorrow.
Bye-bye.